Your stream is running. I think we are recording. Okay, great. I can never see what I'm sharing. Okay, so today I know there were some people asking about. Look, everyone can hear me, right? I think we're good. A lot of people had asked me to do a walkthrough of some of the examples of how to use WeightWatcher. So I'm going to do that today. I put together a Jupyter notebook called. Let's see if I can go down a little. Um, can't quite called WeightWatcher examples, and it's in this. It's in the repo for the experimental code for the experimental code for the paper, for the SETOL manuscript. So it's called SETOL experiments. It's not in notebooks. It's actually in /PyTorch, and I sent a link on the main channel. So all of this you should be able to reproduce yourself. I actually modified the code to run on my Mac OS, and I modified the trainer a bit. So I'll just kind of walk through how this works. So you have to import WeightWatcher. You have to import the transformer library, and then some basic imports. I guess I imported WeightWatcher twice. I didn't even notice that. That's ChatGPT doing that. Then so you're in this. You're going to be in the directory called PyTorch. So you're getting to GitHub. I forgot to tell you, you need to check out the repo if you want to reproduce yourself. Go to the PyTorch library, and in there you'll find a piece of code called Trainer Macros, Mac OS. I can actually do it again to make sure it's there. Yeah, so I just modified the main. So this code is used to reproduce the experiments in the main paper, but I modified the trainer a little bit and added a bunch of features and hooked it up for my Mac OS. If you guys want to run it on a Linux box, let me know. I'll show you how to do it. It's pretty. You just have to set the CPU on PyTorch. That's all, or the GPU. So you're gonna set all this up, and you set PyTorch up. I set this to deterministic false because we're going to be running several versions of the experiment, and we're going to look at computing some error bars. But you can set this to true, and you should be able to reproduce anything in the paper exactly. So, nevertheless, we'll go through basically. Yes, is there a question?
No, I just joined.
Oh, great. Okay,
It's good
great.
to see yourself.
Just some echo.
Okay, great. So I'm just going to go through and explain. So basically, on the Mac, you have to make sure that you basically want to check to make sure that you're. I have a Mac, like a Mac 2, so I run on the Mac 2. You can. What we're going to do is just train a 3-layer multi-layer perceptron on Minced. That's all we're going to do. And so that's what the experimental code does. It sets up this multi-layer perceptron, trains it on Minced, runs the. Can someone? I'm getting some feedback from someone, so if you turn your mic off, that would be great. Thanks. And it's just going to run it on this 3-layer MLP, and it's going to run WeightWatcher for you, and it will save all the results. And we're just going to kind of look and see what the WeightWatcher results look like when doing this. So an example is you can create the model, and I'm just going to make a deep copy of it now, just to have a copy. I'm going to show you how WeightWatcher works. You turn on WeightWatcher, you give it the model, so model equals M0, and you say describe, and what it does, it gives you a data frame. It outputs a data frame, and in the data frame, it has the layer ID. It assigns a unique layer ID that it needs. So if you want to specify things by layer, it has the layer ID. It tries to figure out the name. In this case, the names are OP1, OP3, and OP5. Not particularly insightful, but if you download models from Hugging Face, they'll be reasonable. There'll be names, and you can kind of figure out if you're looking at a transformer what the various layer names are by looking either at name or long name. Then there'll be M and N. It's an N by M. It's an M by N matrix. N is always larger than M, and M sets the number of eigenvalues. So typically, you want this value to be like greater than 50. The tool itself actually sets it to be greater than 50. I mean, the code sets it to be greater than 50. If you have less than 50 eigenvalues, it's kind of hard to really get good statistics on what's going on. So here, when we run the code, we're just going to look at the first layer, FC1, which is a 300 by 784 layer, and the second layer, FC2, which is 100 by 300. That's what we're going to do. we're not, okay, so let's go on. There's a little, this, we don't need to worry about this. This is below. So first we're going to do is look at the initial random matrix. So when you set up, when you set up a model, you're going to have some initial random matrices. They're usually like Gaussian or truncated Gaussian random matrices. And something you have to understand is that you can fit anything to a power law. Like anything can fit to a power law. And so you have to, but what I want to show is if you try to fit a random matrix to a power law, using Marchenko-Pasteur theory, here's how you would analyze it. Recall that we created this deep copy of the model, M0. Nothing's been run yet. It's just initialized. You can set the layers. So we're going to set layers equals 3. Okay, so this is this third layer, right? This is the FC1. We're just going to take a quick look at it. Plot equals true, and we're going to say randomize equals true. And what randomize equals true is going to do is it's going to randomize the weight matrix element-wise. And we're going to be able to see what the random matrix theory says if you randomize the matrix element-wise. So you see, if you start with a random matrix, alpha is really large. Typically, alpha, if it's greater than 8, it's probably, there's nothing there. It's just a random matrix. There might be some signal buried in the noise, but, alpha should be between 2 and 6, maybe 2 and 4 even better. But these are the basic plots you get when you run WeightWatcher. You get a plot of the spectral density. You get it on a linear scale. You get it on, so this is what it would look like. It will try to do the power law fit anyway to this random matrix. You get nothing. You're going to get a plot that says DKS versus X-min. This plot's going to tell you how high quality the power law fit is. DKS is a quality score. It's a Kolmogorov-Smirnov distance. So you'll get a plot, and the minimum value on this plot determines where the start of the power law is. So this is lambda min, which is the smallest eigenvalue, which starts the tail of the power law. So if you went up here and you say, here's you thought maybe this is a power law fit, you're fitting the tail of this distribution. So this is just a histogram of the eigenvalues of that layer. You try to fit it to a power law. The code will select this lambda min, which is the start of the power law tail, and it does it by going to this plot and finding the minimum. And then, you might get a plot like alpha versus lambda min. How sensitive is alpha to lambda min? And obviously here, the alpha is huge, so it's not particularly meaningful, but this is what these plots are. Then you'll get a plot which is random. The random is, what it does is it randomizes the original matrix and it plots the eigenvalue distribution compared to the original. And you can see that if you randomize the matrix element-wise and you plot the eigenvalues, it basically looks, the red and the green look exactly the same. So you can see you really can't tell that this is anything but a random matrix. It also will plot on a log scale. So it will plot the log of the eigenvalues. And this will also, I'm going to make this a little smaller. And this will also be, it plots the log of the eigenvalues. And you see they also look the same. It will also attempt to fit the eigenvalue distribution to random matrix theory with a Marchenko-Pasteur fit. So this red line is the Marchenko-Pasteur fit. And you can see it gives a very nice fit. There's a lot of noise, right? There's a lot of noise in the histogram. But you can see you get a very nice fit of the Marchenko-Pasteur distribution. The variance is 1, which is really a perfect fit for this aspect ratio of Q. And you see you get a nice crisp boundary. And this dotted line is the Tracy-Widom fluctuations. So any eigenvalue which is out here to the right is something which has enough signal that you can tell there's enough signal in it that it's different from what a random matrix would look like. So this is basically what the tool is doing. Now, we're going to go through and we're going to train Minst on using the experimental code. And you can read the code yourself. Here I'm going to train it for, basically you get the training set. You're going to set the learning rate here. It's going to be 16. And then you can set the individual layer learning rates. Here the layer learning rates are just 0.01 times 16. You can set the start and stop epoch. We're going to run it for 50 epochs. I'm going to run it here. Oh, I only ran it once. I thought I ran it 5 times to give you error bars. Typically I would run it 5 times, but I only ran it once here. I forgot to do that. But nevertheless, we're gonna look at what the results are. That's okay. And then if you want, you can restart it at the same epoch. So you could, if you wanted to, you could go in here and say, let's start at epoch 51 and go to 100. And you could even change the learning rate. So the learning rates are a little different. So you might be like 0.2 times LR, 0.1 times LR, and here 0.1 times LR. So it allows you to play with the learning rates, layer by layer. So I just ran one example. We ran 50 times. And, well, there's a little extra here you don't need. And then there's some plots. So there's some plotting code here I put together to help us plot what's going on. So here we're going to just plot the loss and the accuracy. So you can see that the loss saturates, about halfway through, and the test and the training loss saturates. The test loss, actually, it gets to a certain point and it kind of fluctuates a bit, goes down, goes up. So this is just meant to be an example. I'm not trying to reproduce the experiment exactly in the paper. It's just an example so we can see how to use the tool. Notice that the training accuracy, here we see in blue, the training accuracy, it saturates at once. So we're training to interpolation, meaning that we train until we get a perfect result on the training set. And the test accuracy is, I don't know, like 0.0984, That's okay. It's not great. It's okay. So again, this is just a sample run. Now, the first thing I want to point out is when you apply the theory is that people get confused between the weight matrix being heavy-tailed and the eigenvalues being heavy-tailed. And what I want to first point out is that the weight matrix itself is only very weakly heavy-tailed, if heavy-tailed at all. Typically, you can fit it to a Laplacian. You can fit it, but it typically decays a little slower than the Laplacian, the tail, but it's also a little hard to fit. So I'm going to show, I just had ChatGPT put some code together to do this. Here's a plot of the distribution of a sample of the elements. So we're just sampling Wij, and we're going to fit it to a Laplacian. And you can see it's a pretty good fit. It's not Gaussian, it's Laplacian. You'll notice that the cusp region, this top region, is a little hard to fit, but also I'm also sampling it. So maybe the sample has to be larger to fit it, but I just fit it to Laplacian. And then we're going to sort of look at this tail region. And you can see that if you zoom in on the tail, we'll just zoom in on the tail region, there's a little more density in the tail than you'd expect from this Laplacian fit. So this means that, the weight matrix is, for the most part, the elements are Laplacian distributed. They're not power law distributed. But if you go way out in the far tail, you might see the decay might be a little slower than you would expect from Laplacian. So there's a little heaviness there, but not really. Now, if you try to, so again, this idea that it's not that W is heavy-tailed, but if we were to then take this random matrix and try to analyze it with WeightWatcher, what would we see? So again, you run watcher analyze, and you say plot equals true. Again, we're going to just, I didn't want to do that. Okay, sorry about that. You say plot equals true, and you say randomize equals true. And what randomize equal true will do, it will randomize the weight matrix and try to analyze it. So again, here we've run sort of through the whole model. We just took the last epoch. You see that the alpha is 1.872. It's a little less than 2, which is a little interesting. Usually 2 is optimal. And the D value is 0.03. That's pretty good, actually. So this is the eigenvalue distribution on a log-log plot. This is what it looks like on a log linear plot. And sort of go down here. Here's that D versus that DKS versus X-min fit. You can see that when you you're selecting the start of the tail of the power law. You can see there's a really nice sharp minimum right here where it starts. So it's a pretty good fit. Although the alpha is a little sensitive to where that is, but you're basically you're right in this region. So that's a really good fit. Now, if we compare the randomized spectral density to the original, it's very, very different, right? This is not a random matrix by any means, but there is this orange spike. This is something called a correlation trap. It's what we call it. It's some sort of weird rank 1 perturbation in the randomized weight matrix. So this is what I mean by the weight matrix itself is not, the elements are not heavy-tailed, but if you try to look at them with random matrix theory, you might see some weird large eigenvalue appearing. And we're not entirely sure where that comes from. In the paper, we sort of argue that this is sometimes associated with overfitting. And when you see this, when you do this randomized plot and you see this yellow line, which is outside, way outside the red bulk, which is really a perfect random matrix distribution, and outside the Tracy-Whittem fluctuations, it appears to be that this may be a result of this sort of heavy-tailedness, or it could be some weird perturbation. But notice that alpha is less than 2, so it's an indicator that the layer may be overfit. Alpha is less than 2, you have a correlation trap. This is exactly the situation we describe in the SETOL manuscript. You can also try to fit, here's a fit of this to a, you try to fit the random matrix to a Marchenko-Pasteur like we did before. You get a nice clean fit with a little noise. There's the Tracy-Whittem line, which is that boundary. And here's this weird eigenvalue out here, which is really large. So that's sort of the basics of what's going on with how the tool, how to interpret some of these plots. Now I'll go in and just sort of describe some of the various quality metrics. That when you look at the output of the tool, and I fortunately I put it way up here. I didn't mean to. Well, let's see if I can do it here. No, that was a, hold on. That needs to be code. You get a bunch of columns, and I'm sorry, there's a ton of, this is really research codes. There's a ton of columns, and I'm going to go show and throw you in the, I'm going to show you in the details data frame which columns are particularly interesting. So the first thing I did was I modified the code a little bit to implement some layer quality metrics. One is the distance from an it. So the most obvious thing you could do if you're trying to understand if your layers are converging is to just measure how far is the weight matrix from its initial value. So there's a function in WeightWatcher called distance. It's not part of the analyze because you have to give it the initial matrix, but I modified the training code to compute this. And this is just the Frobenius norm of the weight matrix minus its randomized element, minus its initial matrix. So it's just the sum over I, it's the square root of the sum over ij of the weight matrix elements minus the elements of the randomized matrix. And if you were to plot this, versus epoch, you can see that, like, for example, FC1, the distance, as you see more epochs, the distance gets fairly large, and at some point it saturates. So this is, this is where the learning is basically slowing down. If you look at layer 2, however, notice that it saturates a little, maybe at the same spot, maybe a little later, a little hard to tell on this plot. But basically, this is where the learning is saturating. This value, raw delta W, it's delta W. I called it raw delta W because we're using the raw method for the distance. They're all basically the same. This is the distance between W. You can also look at the distance between the bias vectors. Notice that the bias vectors actually stop changing a little earlier than the weight matrix. And again, this corresponds to this sort of slowing down of the training right about here. So you're about halfway through, and you go down to this plot. I'm just kind of eyeballing it. But, it's about halfway through, things stop slowing down. So this is kind of useful. But the point is that you can't detect overfitting. You can't really detect grokking. Like, it doesn't tell you much. So this is the point of the theory, is that, well, how could we actually know when a layer has converged and if the layer is actually overfit or not? And the theory tells you this. But before we get to that, we'll look at some of the other data frame columns. One of the data frame columns in here is norm. So we have the norm, which is the Frobenius norm. And then we have the log norm, which is just the log of the Frobenius norm. Sometimes these values get quite large, so it's easier to look at the log. So this is like buried in here somewhere. Here's log norm, and the norm is down here somewhere. But this is one, and this is just the Frobenius norm. And I think one of the guys here on the channel who was looking at grokking was looking at the Frobenius norm. And, the norm, I don't know what it does. Sometimes it increases, sometimes it increases and it decreases. It's not particularly insightful, but you can see here that the norm in this particular example, the norm was basically increasing for both layers and it stops increasing. And to say, excuse me, this is not the norm. That's not the norm. This is the norm. Sorry. So you can see for FC1, the norm is quite large, and then it stops about halfway through. It stops increasing, and for FC2, it has very similar behavior. There are also these spectral-based norms. So some people like to look at the entropy or sorry, they like to look at the entropy or the spectral norm or the log spectral norm or the stable rank. And the code can, it's running SVD, so you're going to get the eigenvalues of the correlation matrix. And so the matrix, the entropy is just the matrix entropy. It's the sum minus some p log p, where p is the sum of the eigenvalue divided by the sum of the eigenvalues. I don't know if you can read that. The spectral norm is just the largest eigenvalue, and then the log spectral norm is the log of that, and the stable rank is the ratio of the Frobenius norm to the spectral norm. So, and again, you can look at them. Some people like to look at them. You can see we studied this in our early JMLR paper. The entropy decreases. It will decrease for the layers. The log spectral norm, notice that the spectral norm is increasing. This is actually at odds with statistical learning theory, which suggests that the spectral norm should be decreasing. So you can see the spectral norms increase, and larger spectral norms mean heavier tail distributions. So you're going to get smaller alphas as this happens. The stable rank decreases. Maybe the stable rank is meaningful. Again, it tells you something about what the actual rank is, what the rank of the matrix should be, how many generalizing components there are. But what you'll see in our theory is that we have an exact theory for this. So the stable rank it just doesn't have a lot of granularity. But nevertheless, the tool can compute these things. Now we go to the HTSR metrics. So here, I'll try to zoom in a little. Here sorry about that. We're modeling the spectral density as if it can be fit to a power law. So we have this, give me a second here to go back down. So I lost the, where are we? Here we go. So we're modeling the spectral density. You just have a histogram of the tail. So you have the tail of the eigenvalues, scales as lambda to the minus alpha, where alpha is the power law exponent. Notice that the tail is between lambda min and lambda max. Now, typically, lambda max is the largest eigenvalue, but not always. Sometimes there are these extra eigenvalues I call dragon kings, which stick out of the tail, and you have to throw them away to get a better fit. We'll talk about that a little later. But right now, just realize that the tail is this part of the eigenvalue distribution, which we think can be fit to a power law. And there are various metrics. Alpha is the basic metric we use. Alpha weighted is just a scale weighted version of alpha. It appears in our Nature paper, and we talk about it a little bit in the SETOL paper. We don't worry about that now. D is the KS distance. That's the quality of the fit. X min is the start of the power law tail, so lambda min. The number of PL spikes, that's the number of eigenvalues in the tail. So it's the count of lambda greater than or equal to lambda min. And then this thing called the IMPI soft rank is something defined in the HTSR paper in JMLR. It's just the minimum eigenvalue relative to the largest eigenvalue you would find if you were fitting the distribution to Marchenko-Pasteur. We won't talk much about this, but these are the primary data frame columns: alpha weighted, D, X min, num-PL spikes, and W soft rank. The soft rank's described in the JMLR paper. Let's take a look at alpha for this run. So here we see something very interesting, right? So now we get to the meat of things. Alpha equals 2 is your optimal value. That's what the theory says. When alpha's 2, the layer is at its ideal state. It shouldn't be larger or smaller. Here we see that in this particular run, FC2, it gets about halfway down, right about halfway through where we think the convergence is happening. Alpha stabilizes around 2.1. If you train it for a little longer, maybe it jumps down a little. So that's not bad. That's not bad. That's pretty close to 2. It's not perfect, but it's not bad. In this particular one, FC1, however, dropped below 2, and it goes just a little bit below 1.9. And remember, we saw this rank 1 perturbation in the random matrix, which we think is a correlation trap, and I suspect that may be contributing to this alpha being a little less than 2 and a little overfit. So this is pretty typical. And the idea of sort of this set of code and what we're trying to do is, can you do things like modulate the learning rate to try to get both of these optimal to 2? And some of the stuff we've tried to do, we've had some success at that, but it's not particularly easy. And it's not particularly obvious that for any architecture that every layer will converge to 2. Maybe the architecture is too big. Maybe it's not well designed for the data set. But this is what the theory is telling you, that in theory, both of these layers should concentrate at 2. Now you can count the number of spikes. By number of spikes here, we can make a plot. So to get the number of spikes, the numpl spikes, you would say watch or analyze. You say layers equals 3. And we say impy fit equals true. And if we do that, again, we get this plot we saw before. We go down. Here's the impy fit to the layer 3. And on the linear scale, the sigma is quite small now. It's not 1.0. We've lost a lot. In other words, this means that you've lost quite a lot of density in the bulk. And this is the impy fit. And what you see here is this large number of eigenvalues, which are outside the Tracy-Whittem line, outside this bulk. There's actually 175 of them. That's the number. That's the numpl spikes. It's all these eigenvalues which are out here, which are described in the JMLR paper sort of as bulk plus spikes or weakly heavy tail. This is what's going on. But you can see this is a pretty heavy tail distribution. It's not Marchenko-Pasteur at all. So even this Marchenko-Pasteur fit, it's a pretty bad fit. Now, if you plot the number of spikes, you would see that, again, the number of spikes tend to increase with decreasing alpha, and then it sort of saturates. And the same thing for FC1, for FC2, the same thing. Although the number of spikes doesn't change. It sort of fluctuates a bit. It doesn't change much, and it sort of saturates. And this is where alpha is saturating. Okay, now we get to the SETOL metrics, this new paper that we're publishing. Here, what we're making this claim is that not only when a layer converges, not only is alpha equal to 2, but you have this thing called the trace log condition. The trace log condition is actually, for those who know some physics, this is a condition of exact Wilson renormalization group. So it turns out that the theory says that when a layer is converged, it satisfies Wilson exact renormalization group. You have this trace log matrix. X is just basically the weight matrix restricted to what is now called the effective correlation space. It's like the power law tail. And if you were to take the trace of the log or the log determinant of this matrix, you would take the log of the product of the eigenvalues in the tail, and you expect that to be 0. So what happens is, just like before, when the power law fit tries to find the minimum, the start of the tail, the dead X method will attempt to find the start of the effective correlation space described in the paper. There are a couple of blog posts on this if you want to look and understand better. And what are the metrics you get? You get dead X num, which is the number of eigenvalues in the tail, and then you get this dead X value, which is the value of the power law. So before, recall, there's this power law that starts here. This is the start of the power law tail. There should be a plot here. Oh, I didn't run it. I'll show you how to run this. If we do this, we go down here to SETOL, and we can actually plot this. We say dead X equals true. Give it a second. Okay, we get the plots. Here's your power law fit. Oh, wrong spot. Go down here. Oh, here we go. We get a dead X plot. So we get this plot where now the purple line is the start of what's in the paper described the effective correlation space. And the red line is the start of the power law tail. And the theory says these two things should overlap each other. And notice here that the red line is a little to the left of the purple line. And that's consistent with alpha being less than 2. When alpha is 2, these two lines tend to overlap. When alpha is less than 2, the red line is to the left of the purple. When alpha is greater than 2, the red line tends to be to the right of the purple. So again, the theory, this is all predicted. This is like all came out of the math and trying to figure out why in the hell HCSR works. We found this independent metric, and it turns out we think this is a condition for a model, a layer to be ideal. Here you can plot, what we do, you can plot the number of eigenvalues in the effective correlation space, which is similar to the power law tail. Similar behavior, there are more eigenvalues in layer 1 than the space in layer 2, just like we saw before with numpl spikes. Now what you can do is you can subtract, and it's not in the, you have to do it yourself. It's not in the data frame by default. I need to add this, but you can compute delta num spikes, which is the dead X number versus the num PL spikes. I'm sorry that the notation's a little goofy, but or inconsistent. But if you plot this, what you find is that this value delta at when the model is ideal, when the layer is trained, this should be 0. So this value, and you see here's the 0 line, and you can tell that for FC1 and FC2, FC1 actually drops below. Remember I said it was a little overfit. It drops below 0, and that below 0 corresponds to this red being to the left of the purple. Remember, this is on a log scale, so you get a big drop. And you can see that FC2 is almost ideally trained. So again, theory says that this number should be 0. So the closer you are to 0, the closer we think the layers are converged. So this is what's going on. And the idea is that you can look at various models. You can look at the layers in your models. You can plot epoch by epoch, or you can make histogram plots, and you can tell how close your models are, how close the individual layers are to convergence, or even if the layers are overfit by looking at these various metrics. The last one I want to talk about is this idea called Dragon Kings. There is an idea that, again, this notion that when you fit the power law, there's a region where the tail, there could be some weird eigenvalue out here, and when you include it, it screws up the power law fit. We call that a finger. And why it's called a finger is because it looks like a little finger on the plot. I don't have a good plot of it here, but basically the tool will attempt to pick the tail, and it will try to throw away these little fingers. And I think that I have this conjecture, hypothesis that these are Dragon Kings. There's a guy named Dito Sornay who has worked out this idea of the Dragon King theory. And the idea being that when you have power laws, sometimes you'll get large eigenvalues out here, which are some kind of dynamical driver of the system. And I think that's sort of my suspicion of what's going on. So we can look at this, and basically you compare the raw alpha. If you want to see if there's a Dragon King, you compare the alpha to the raw alpha, and you see here they see the same. And there's another metric called number of fingers. And if we were to look at number of fingers here, we can do that. We could say here, we pick the last epoch of our data frame and say num fingers. And num fingers is 0 for each layer. And again, there's a blog post where I sort of describe what this fixed fingers feature does. And I make this argument that in Mistral, it appears that there are lots of fingers. A good example is Mistral. If you look at Mistral, you would see this. Maybe we can, yeah. So here's an example with Mistral. Here's an example, but if you were to make a histogram, you would see here's the alpha and the raw alpha. You can see that the alphas that are fixed are much, much smaller on average than the alphas that are raw. So you get this idea that you fix so this is one of the conjectures I have with Mistral. It just seems to have lots and lots of fingers. And here's an example of, okay, here, well, that's not good. Here's the finger. So this idea that when you have this extra eigenvalue out here, it screws up the fit. See, so if you have like this weird outlier and you try to fit alpha, you get an alpha which is much larger. This purple line is much larger than you'd expect. And when you remove it, you get a nice solid fit with the red line. So you have this, so you have to, when you do a power law fit, you have to pick the start of the power law and you have to pick the end of the power law. And WeightWatcher does all this for you and attempts to give you the best fit. And again, there's another example of the DKS. When you see fingers, you get these spurious fits and it tends to screw things up. So another thing you can do is, well, I'll show here. So another thing you want to do to check whether you're getting good results is all of these quality metrics are roughly the same. Like they all should behave in the same way. So here's an example of plotting raw alpha versus random distance. So the random distance you get by saying randomize. If you want to check to see if things are going correctly, plot your alpha versus the rand distance. Here's raw alpha versus rand distance for Mistral, and here's alpha versus rand distance. You can see that the raw alpha has like some crazy dependence on this, whereas the alpha that we fixed has good dependence. So what does this mean? It means that the smaller the alpha is, the larger the random distance is, meaning that you're actually the smaller alpha is, the more correlated the system is, the farther it is from a random matrix. So you can always check your alphas for a big model by plotting the various metrics against each other. They should all have basically the same behavior. There's going to be some scatter, right? There's a lot of scatter, there's noise. The power law fits are hard to do. You're going to get a lot of scatter. But the idea is you can always check to see if things are working correctly by doing these kinds of plots. I won't go into the Dragon King theory. So there are some. So that's sort of the stop there of, sort of how you can use the tool, and just kind of a run through of the various layer quality metrics in this huge chunk of things. There are some other things like vector entropy metrics and vector localization metrics, which you can look at the bulk versus the tail. I didn't talk about that, but if somebody's interested in that, I can go through it. I'll sort of stop there, and I've got a couple other things I want to talk about, but if anybody has any questions, if you have any questions, let me know. Otherwise, I'm going to give you a couple more examples. All right.
Is the Dragon King
Go ahead.
effect and so about the Dragon King effect and the fingers, could they be a consequence of grok circuits?
Of what?
For example, of grok circuits. So if some circuits in the neural network got hyper generalized, and we have a large spin glass structure, and we have these discrepancies because of that.
I'm sorry. Say, I just didn't get the first term. They're due to what? Say it again very slowly.
Okay, so
I understand the spin glass stuff. I just couldn't understand the word you were saying.
Yeah, about the Dragon King effect and the fingers.
Yes.
Yeah, if they are consequence of generalized circuits.
I'm sorry, I don't understand. Can you say it again? Of
Generalized circuits within the network.
generalized
So if we
sequence.
yes, circuits.
Circuits.
Yes.
Maybe. I don't know. It could be like, I mean, the one of the things you have to realize is that when I use WeightWatcher and I talk about things like Dragon Kings, this is complex systems theory. So we don't know we can observe this phenomenon. We observe power law tails, we observe renormalization group, we observe Dragon Kings. We don't ascribe a mechanism to them. So we don't know what the mechanism is. So there could be a mechanism inside the model causing the Dragon King. We don't know what it is. We don't know what the mechanism is. One of the things about complex systems theory is that it allows you to describe universal properties, these sort of universal characteristics. Random matrix theory has universality, phase transitions, critical exponents, without understanding the underlying mechanism. I would love if someone can figure out the mechanism. I don't know the mechanism, so it could be. But this is something that sometimes is sometimes a little different than what a lot of people have do in statistics or machine learning, is that they're always trying to do mechanistic interpretability. They're trying to find a mechanism for something. I'm not trying to find mechanisms. I'm trying to give you quality metrics that you can use. And then if you can figure out the mechanism, let me know. We'd be very interested. So another thing so I hope that was helpful. Are any other questions? We're going to give a couple more examples if there are any other questions.
So, Charles,
yes.
In terms of difference between the measures of alpha and Detex num,
yes,
was there a fundamental difference, or basically they were equivalent?
Well,
because, based on the figure.
Yes. So we tried to derive a theory. I'm trying to derive a theory of learning and explain where the alpha comes from. And in doing this, we can find that plot. In doing this in the paper, I don't have the plot. All right. Well, I'll just talk. My suspicion is that the alpha power law is a universal critical exponent that's associated with the renormalization group transformation. Because typically when there's a renormalization group, there's some critical exponent associated with one of the thermodynamic parameters, but we haven't been able to prove it. I haven't been able to prove that alpha equals 2 is the critical exponent. So we discovered it empirically. Like in deriving the theory, I realized I had to do this volume preserving transformation. And I said, well, and it leaves these extra terms in the theory. So I said, wait, maybe it just works empirically. So I checked it empirically, and it turned out it does work empirically. And then I realized, oh, this is renormalization group. And I sort of re-derived the Wilson renormalization group from scratch, not trying to find, there's a blog post that says, not realizing that, just from empirical observations. So here's this sort of picture of, you have this effective correlation space. It turns out that it appears to be associated with the start of the power law tail. And it turned out when we did the experiments, it matches perfectly. But I'm not sure why. Like, is it just, I have this, like, it's either really deep, it's a really deep fundamental thing about what's going on, or it's something trivial, and I haven't figured out why it's trivial yet. Yeah. And I'm terrified that it might be trivial. Right? It could just be whenever you fit alpha equals 2, it turns out that this condition holds, and there's some relation I don't know. And it's but so far it seems to be like something very fundamental.
So based on that, up to now, it's sort of a empirical equivalence.
Yes, it's an empirical equivalence. You can derive, well, there is something else. When you derive the renormalization group transformation, there is a branch cut in the free energy, if you know some physics, and that does seem to correspond with the tail. So it does seem to be that the renormalization group theory is correct, because you get this branch cut, and the branch cut corresponds exactly to this tail. But I don't know how to predict the critical exponent. Right? I don't even know how to derive the where it would come. Like we can derive the expressions, but it's not clear that alpha equals 2 is exact. So right now it's mostly empirical. But theoretically, you do if you model the system as an inverse Wishart distribution with alpha equals 2, you find that there's a branch cut in the theory, and it corresponds perfectly with the start of the tail. So there is some good theoretical reason for it, but it's not, maybe when I retire, I'll be able to figure it out. But maybe you can figure it out. I don't know how to derive the exact value of the critical exponent yet.
So where is that exact statement made in the SETOL paper?
Which one?
The latest paper.
Which I'm happy to load the paper.
This is statement branch cut.
It's in section 5.6. So there's a section 5.6. I go through the branch cuts, and I sort of give this. It's not, this part is not quite. The plots are still kind of screenshots, but it's all there.
Yeah.
I was quite surprised. Like that was like my when you work in the SETOL paper, you have to work out this integrated R transform, and the R transform is a complex function, and it turns out it has a branch cut exactly where the tail starts. That was very encouraging.
Okay.
Right.
Yeah.
But it only happens when you have when you model this. Well, you can read the paper and let me know what you think.
Yeah.
All right. Any other questions? I do want to go through one more example with you guys, because you asked for examples. There's an example. If you take a look at instruction fine-tuned models, this is really neat. So it turns out that like if you plot here's an example of find a good one. Yeah. Here's Mistral, Quinn, and Llama. Okay. So if we look at, say, can we get this here? Okay, if you look at Mistral, like say Mistral 7B, or Quinn 2.57B, or Llama 3.18B, and you plot a histogram of the alphas, most of them lie within this range, 2 to 6, I call the safe range. A lot of them, however, have, all the base models typically have a bunch of alphas that are larger than 6. And what I suspect is going on here is that it's just easier to train a big model than it is to train a small model. It takes more epochs to train a smaller model. The larger models have a much, in sort of high dimensional statistics, you expect that the landscape is just easier to traverse using SGD, and you're able to get a good solution. But it turns out that a lot of the layers are just, they're underfit. Like the model's bigger than it needs to be, which is why people, I think, can distill the model so effectively. Now, it turns out if you look at, by the way, if you look at like Llama versus Quinn, for example, here, Llama has about 25% of its layers underfit. Quinn has about 20%. DeepSeek only has 10%. I don't have DeepSeek on here, but that turned out to be true. So it appears that the DeepSeek guys seem to have, at least in the lens of WeightWatcher, seem to have done a better job of training a smaller base model, even though it's huge. You know? The other thing is if you look at the instruction component, so you can take a model and you can do instruction fine-tuning, and you can use WeightWatcher to subtract off the instruction component. And you do that by just specifying, see if it's in this blog post. It's in an earlier blog post. You just specify the base model, and WeightWatcher will subtract off the instruction component. It turns out that for most models, the instruction components satisfy the HGSR theory, that all the alphas lay between 2 and 6, and a lot of them between 2 and 4. And you can see this with Mistral 7B. You can see it with Quinn. You can see it with Llama. There are some exceptions, but for the most part, so you can see this. And moreover, if you plot the base model alpha versus the instruction fine-tuned alpha, like here's an example of Llama 3170B, and we plot the instruction fine-tuned alpha versus the base model alpha, you can see that for the most part, when the base model has a smaller alpha, the instruction fine-tuned component is smaller. So like here, alpha equals 6. The base models are around 3. You know, they sort of interpret here. You don't see alphas way up, and you see a few, but there's a nice trend showing that as the base model alpha gets smaller, you will see smaller alphas. It's not perfect. There's some noise up here, and there's even cases where the base model alpha has no effect. But I think generally speaking, you see this sort of trend here. The better the base model is trained, the better the instruction fine-tuning component is. Up to a point, and then you sort of overfit a little bit. Yes?
Yeah, of course. No. Mix it. Yeah, I'm coming.
Okay. All right, someone's got to go. So this is another example I wanted to show you guys. You can use, it turns out, and this is actually comes right out of the math, that why can you analyze these components separately? Well, because they're, if you treat them like in the math, you have this sort of these R transforms. The R transform is additive for random matrices. So we sort of argue that you could subtract off one component and analyze it individually, and it seems to work. And we've had some cases where we've had some models where it doesn't work. We don't know why it fails. Sometimes it fails. We don't know why. We typically only see it failing in smaller models, but there have been examples, like I worked with a group in Poland, and with this sort of strange effect where they were trying. Oh, I lost it. Well, I'll just say it in words. They were trying to mimic the training for a model called Solar. And the Solar model shows the HGSR theory predictions exactly as you would expect, and their model did not. We don't really know why, but these are the kind of things we're trying to figure out. So, and I give some examples. So on the blog, I give some examples of bad. So there are cases where it works. So it works every time. Llama, Falcon, Mistral, Solar. And then you get to this, there is like a counterexample, like some of the Llama 3.2, Llama 3.2.1b, Llama 3.2.3b. For some reason, the smaller 3.2 llamas do not satisfy it. So I don't know what they did in the Llama 3.2, but somehow the small models didn't satisfy. And then as you get larger, the larger models tend to behave much better. So this is an example, and there's some examples on the blog post of how you can use the theory to, if you're doing instruction fine-tuning, or maybe you're doing reinforcement learning, you can use the model, you can use the tool to analyze your updates, and I'd be very interested to see what you find. Maybe is the theory useful? Do you find that on generally the instruction fine tuning, when you have smaller alphas on average, does it give you better performance? Things like this. That would be very interesting, and sort of release the tool so people can try doing stuff like that and give us feedback. Let us know what you find.
I think the 3.2 and 3.3b could be because they are distilled from a multimodal larger model. Because the larger models of the newer llamas are multimodal. I'm not sure.
Yeah. The larger in the llama model when they do this, but we that's a good question. I haven't looked at enough of the distilled models coming out of like the distilled components to know whether that's a general case, but that would be something interesting to look at.
Yeah, I think so.
So this is sort of a walk through the tool, how you use it. Phil, I don't have a lot of time to write. We don't have a lot of documentation, but we have the Discord channel. Just ask anything you want when you're using the tool, and we'll try to answer your questions on Discord. And hopefully, I'll clean up this notebook and check it back in. Hopefully this is useful to you. So there's the hour. We got about 5 minutes. Any other questions? The only other thing I might discuss is maybe we have a chance to look at we see if I can find it here. Well, there are some examples we've had of grokking, so you might want to take a look at some of the grokking stuff that's been going on. There's a couple people on the channel doing some grokking experiments, and they've got some very interesting results where you can really see in grokking, you can really see this really nice phase transition that occurs. You can see the alphas. You'll see the grokking going along, and all of a sudden, when the grokking kicks in, bam, the alphas increase on the layers, and then they decrease very rapidly. And so you can really see the phase transition from grokking using WeightWatcher. So that's kind of cool. So anyway, I'll stop there. I'll upload this a little later today. If anyone has any more questions, you can ask me here, or you can just ask me on Discord. Okay, great. Well, thanks again for joining us.
Basic instructions.
I'm going to stop recording.
Thanks, Joe.
Hey, thank you. Thank you.